Before going off the deep end and delving into how I'm going to make the VDG better, I need to talk about the other half of the hardware equation, the SAM, or Synchronous Address Multiplexer. This single chip is responsible for generating the system clocks, decoding the address bus from the CPU, deciding which device it is trying to communicate with, encoding RAM address requests, refreshing DRAM, and keeping track of the video address. In pretty much any other 80s home computer, this would have been called a ULA and served double duty as a video generator, but not here. Instead, we have a device dedicated to a small number of activities that would otherwise generate a sprawl of logic ICs. Generating the clock signals is probably the simple bit at first glance, but even that is more complex than you'd think. The master clock is divided into 16 cycles, and almost each cycle triggers something or other. To start with, the CPU clock is a quadrature system with two signals that are 90 degrees out of sync. The Q part is the warm-up act and prepares the CPU for action. The E part is where the magic happens and everything changes state. The CPU is only active for the high values of Q and E, the low values are used to provision the VDG, and when the VDG isn't busy, the horizontal sync, the low values are used to trigger DRAM refresh cycles. It also divides the master clock down into the video clock, with 4 video cycles for each 16 master clock ticks. To make things more complicated, the SAM has 3 different CPU speeds: slow, address-dependent fast, and full fast. In the fast modes, the CPU aims to run at double speed, but where it is address dependent, that only applies when it isn't actually accessing a slow device, generating video, or performing a RAM refresh. Keep in mind that many instructions have dead cycles in terms of memory access. In full fast mode, neither the video access or RAM refresh are performed. Video is still generated, but it will be garbage, and in theory, unless in SRAM mode, the system memory should corrupt pretty quickly. Looking at this from the outside and treating the entire chip as a black box, as defined by Motorola, we need 6 inputs: the address bus, read-write, DA0, horizontal sync, plus a pair of pins driving the master clock. On the outside, there are 8 or 9 distinct signals: the device select, S, DRAM multiplexed address, Z, RAS0 for lower bank, RAS1, upper bank, CAS, both, write enable, quadrature clock, Q and E, and the video clock. RAS1 is actually sharing a pin with Z7, and which signal is used depends on the memory configuration. In the interest of simple, I'm going to optimize things a bit early, so for my purposes, I only need a single master clock pin, as I'm using an oscillator rather than just a crystal. I also don't need RAS1, as the memory will always be a single bank of 64K, so Z7 is always Z7. I'm using SRAM, so I don't need CAS either. The next bit though is less obvious. I need an external vertical sync, FS. The 6883 infers this signal internally, which is all well and good, but since I'm in control of the spec, I can simplify and just accept the real vertical sync fresh from the VDG. I'm also going to add an external reset signal, another one inferred by the original logic. And again, I can simplify things by making it an input. Internally, let's start with a clock generator. It has just 4 inputs: oscillator in, DA0, clock speed register, R, and reset, plus 3 outputs: the 2 quadrature clock signals and the video clock. It converts the 14 MHz input clock into the 0.9 MHz quadrature clock and 3.6 MHz video clock. The quadrature clock can also be at 1.8 MHz depending on R, and the change between normal and fast just needs managing. Thankfully, a state machine that accurately describes all of this behaviour is defined in VHDL already, along with the rest of the functions of the SAM. I've converted that state machine to Verilog, because mixed language implementations cause simulation problems, and adapted it to suit my purposes. There are a few things going on here. The obvious is the quadrature clock and switching between fast and slow modes. I need to generate a memory strobe to latch the video memory for the VDG. This was originally the RAS signal, but I don't technically need RAS or CAS anymore, as I am explicitly and exclusively using SRAM. I have to manage the internal reset condition and how it affects the state, and, for those that have been listening to previous updates, manage the synchronization between the SAM and VDG. Historically, this was done by freezing the video clock until the right clock phase is reached, but because I'm integrating the VDG and SAM in a single device, I can now tell the VDG what state it is in, so it is the VDG that synchronizes rather than the SAM. Thanks to the faster access times for SRAM, I can also squeeze the fast mode to maintain a video signal. The next simple trick in the SAM's list of responsibilities is just that of decoding the CPU address value into a device select. The SAM defines 8 different devices, itself being one of them. This breaks the memory up into distinct, unequal sized chunks and helps the SAM to ensure correct DRAM addressing. The module accepts the address, read-write, and memory map type, and outputs the device select signal. Internally, this is literally just a set of if-then-else conditions that decode the memory map into devices. In addition to the SAM itself, there are 3 different ROM slots, although they could equally be RAM or I/O devices. 3 different peripheral I/O devices, each with 32 bytes of address space, and finally the system RAM. The PIO and SAM blocks are always respected, and the last 16 bytes of the address space will always be directed to ROM block 1, but the choice of RAM or ROM is otherwise governed by how the SAM has been set to operate. The address space can be all RAM, so 64K, less the PIO and SAM addresses, which add up to 256 bytes, 50/50 RAM-ROM, 32K with a RAM in the lower half, with a paged RAM toggle where the upper 32K out of 64K RAM is remapped into the lower 32K. The RAM access is normally further complicated by a configuration for memory size, either 4K, 16K or 64K of dynamic RAM, or 64K of static RAM. For my purposes, the answer is always 64K of static RAM, so this bit of configuration is ignored. The device select is exposed externally as 3 control signals that expand to 8 control lines. Internally, the device select is also used to inform the address-dependent part of the CPU clock. The memory size also feeds the RAM address encoder, whose job is turning a 16-bit address into 8-bit row and column addressing for DRAM. The CPU clock decides which is presented, row or column, and also generates the clock signal for the row and address latch signals, RAS and CAS. As far as I'm concerned, there is only one memory size, so I can ditch that signal from the design. This also means I don't need RAS1 or CAS. I still need RAS0, not for memory access, but to synchronize memory latching instead. One detail that is needed, and best not forgotten, is that this is all synchronized with a clock signal Q. Another important feature that keeps turning up is configuration. The SAM maintains a set of internal registers that define how it behaves, but the real trick is that the SAM has no visibility of the data bus. The only way to change the SAM registers is bit by bit, using even addresses to clear a bit and odd addresses to set them. For example, the CPU clock speed is controlled by a 2-bit register, R. This needs 4 addresses, FFD6 to FFD9. The first 2 addresses control the first, lowest bit of the register. The second 2 addresses control the second bit. This is somewhat cumbersome to work with, but without a data bus, there isn't much option. There are 6 accessible registers that operate like this. 3 bits for video mode operation, 7 for the base address of the video memory, 1 bit for the memory page, 2 for CPU speed, 2 for memory size, and 1 last bit for the memory map type. A total of 16 bits of register and 32 bytes of address space. The access and control of these registers is handled by a dedicated module that accepts the Q part of the quadrature clock, address, read-write, and reset. Output is just the value of the managed registers, V, video mode, F, video base address R, CPU speed M, memory size P, page, and TY, memory map type. And as I mentioned earlier, there is only one memory size in this design, so I can lose the M register. The SAM also maintains an internal 15-bit video address register, B, that cannot be directly accessed. The base address register defines the starting address for each video frame at a resolution of 512 bytes, which together gives access to the entire 64K address space, but the exact value of the address register is hidden. It increments every time DA0 transitions from high to low. Effectively, DA0 is the least significant bit of the register, extending it to 16 bits. The internal video address register is handled in its own module that accepts V, DA0, F, and HS as input, and outputting just the current video address B. I add in the vertical sync FS as an explicit signal for simplification. Internally, there are some dividers and counters that provide a mechanism to repeat rows of video data when a horizontal sync is received. In text and semi-graphics modes, each row of data is repeated 12 times. Some bitmap modes require a row 2 or 3 times. The dividers, in combination with the video mode register, define how many bits of the video address register are reset on a horizontal sync when repeating a row. Whenever a vertical sync is received, the video address is reset to the base address. The horizontal sync always clears a number of bits from the video address register regardless of repeat, unless video addressing is set to DMA mode. Remember this nugget. If the least significant bit of the video mode register is clear, the SAM will clear bits 1 to 4 of the video address register, effectively giving the register a 32-byte resolution on a horizontal sync. If the same bit of V is set, only bits 1 to 3 are cleared, which equates to a 16-byte resolution. If the row is set to repeat, the next uncleared bit is preserved, otherwise the address increments as normal. When V is set to DMA, no bits are cleared at all. This typically means that mode 6 and 7 behave identically on paper, but the VDG has a little trick up its sleeve. DA0 continues to count past the right-hand edge of the viewport. In mode 6, this is hidden as the relevant affected bits are cleared. In mode 7 though, this means the extra bytes are hidden. This would be really useful for horizontal scrolling if the base address could be controlled on a per byte resolution, but sadly this is not the case. It still has its uses, but not what you might hope for. The original SAM 74LS783 maintains an additional 7-bit register for managing the DRAM refresh. This increments on every horizontal sync and triggers a count of 8 memory refreshes. Going off on a tangent here, the 7-bit register allows for 128 addresses and is targeted towards 16K memory chips. So how does 128 address refresh all the memory? The answer is that the 4116 and other memory chips specified perform a row-only RAS refresh. When the 16-bit address is encoded into the RAS-CAS row column addressing, it explicitly specifies the row first, then the column. Rather than refresh all the memory cells, the RAS-only refresh just needs the row to specify, and the DRAM chip itself does the rest of the work. The headache comes with larger capacity RAM chips that need 8 bits for row and address. A 32K chip can still operate on 7-bit row, but a 64K chip needs 8 bits for both. Some manufacturers deliberately made their chips 7-bit compatible, and this is great for upgrades and mandatory for an original Dragon 32. The later versions of the SAM, 74LS785, actually fixes this and uses an 8-bit counter, but also pushes the refresh timing past the 2 millisecond maximum for a 4116. But thankfully, the 8-bit 256 cycle chips were designed with this in mind and allow for a maximum of 4 milliseconds. Now that I've mentioned all this, the whole lot is irrelevant to this project. I'm specifying SRAM only, so there is no refresh cycle. That means no refresh counter. This also raises another point. If I'm only specifying SRAM, then I don't need the multiplex RAM addressing. I should just need the main address bus, and this is almost true. The fly in the ointment is the P register. This single bit register can have control over the most significant bit of the address bus when specifying RAM in the mixed RAM plus ROM memory mode. So I need 1 bit of Z at least to replicate this behaviour. What I also have is a crystal ball telling me I will need more bits in the future, and for now you will just have to take my word that I do indeed need those extra bits of Z. Putting all of the remaining components together, we have a bit of a wiring mess. Unlike the VDG, there are outputs that influence components before them in the flow. I've isolated functions as much as I can, but there is only so much that can be done. There is one signal missing from most of the components in the diagram, the main clock. The original SAM datasheet doesn't explicitly state when data is latched, although it can be inferred. There are a number of delayed triggers that suggest the answer is that there isn't a single synchronized clock. My version, however, uses the master clock to synchronize transitions. This has a slight side effect. Where the logic is layers deep, the number of clock ticks to fully propagate a change can cause problems. Some of this can be mitigated with combinatorial logic that propagates faster than latched values, but the timing on these circuits has to be then constrained to make sure the signals arrive in order. I can improve the situation further by doubling the master clock. This narrows the timing gap for propagation, but means the main timing state machine needs twice as many states, all of which is doable with a little effort. Once again, as with the VDG, that's it. A surprisingly simple design, at least if you ignore the ugly complicated bits of just 5 functional parts. Those of you that have been following my posts and updates will be wondering, why has this taken so long? The answer is manifold. First of all, I spent way too much time on the VDG, changing my plans on what to do with it and how it will work once I start expanding and improving it. Second, I only settled on including the SAM quite recently, just a few months ago. And finally, so far, all I've shown is the default functionality with some adjustments to simplify the design once the VDG and SAM share the same silicon. It takes me quite a while to prepare each of these video updates, and I was already quite a way down the road of customizing everything even when I started. Plus I have this thing called a job, which means I only get to work on this for a short while each day, not to mention all the other things I have to do. Putting all these things aside, we're actually now at the juicy bit of what I can do with the project. Why I need something more capable than the basic max CPLD I started with, and what it actually means for the future. The next update will look at the enhancements in the video side, and a look at the Tandy Coco 3 gaming chips that led this way. Until then, don't forget to leave your comments and feedback.